Good morning, friends. Today we are going to discuss about Fermat's principle. Fermat's principle. Now, Fermat's principle is a remarkable and very important principle in optics. It is proposed by Pierre de Fermat in 1658 and around in 1650s. So, it is very important. It has very important role in the field of geometrical optics, and this principle explains one, the rectilinear propagation of light, rectilinear propagation of light, and about the laws of reflection, and the famous laws of refraction. We have geometrical optics consisting of we are representing the optical light rays by using some lines, and we are expressing or explaining the certain laws and corresponding to the optics by using the lines and explaining it. So, before entering to the statement of Fermat's principle, we have to know about optical path. We can say that or we can explain it on the basis of the word itself, optical path, which is the path followed by an optical light ray. For understanding about the optical path, let us consider 2 points P and Q. P and Q are some points, and the distance between P and Q is is S. S is the distance between P to Q, and a light ray is passing from P to Q through the distance S, and let us consider the velocity of light ray is V. This V is the velocity of light ray, and the refractive index of the medium containing P and Q is mu. I am denoting the refractive index in mu. Some other textbook the notation is something like N. What I mean is the optics by Ajoy Ghatak is following the notation of N for refractive index, and some other textbook also following like that. Here mu on or N, where mu is the refractive index of medium. Refractive index. So, from basic theories, if an object is moving from P to Q, we have if S is the distance between P and Q and V is the velocity, we can write it as the velocity V will be equal to S divided by T, where T is the time taken to move that object from P to Q. Similarly, we can say that if light ray is passing from P to Q, we can express that this light ray consumes a time T for covering the distance S at the velocity V. Then from this equation, let us mark this equation as 1. Then we can write it as S, where the distance between P to Q is V times T, V into T. From the theory of refractive index, this is marked as 2. From the theory of refractive index, we can write it as mu, which is the refractive index, is the ratio of velocity of light in vacuum to the velocity of light in medium, where C is the velocity of light in vacuum. Velocity of light in vacuum. From mu is equal to C by V, we can write it as, this implies V will be equal to C divided by mu, and I am denoting this equation as 3. Then substituting the value of V in equation 2, we can write as S is equal to C divided by mu into T, which implies mu times S will be equal to C times T. Mu times S is equal to C times T, where C is the velocity of light in vacuum, which is a constant, and T is the time taken to move that light ray from P to Q, and mu is the refractive index and S is the geometrical distance. From this equation, mu into S is equal to C into T, we can write that, or we can interpret that this quantity C into T corresponding some quantity which is the equivalent distance in vacuum that light ray, the particular light ray, can travel in vacuum, or the quantity C into T is the equivalent distance in vacuum when light ray corresponding to the geometrical distance S. That is, if a light ray is traveling in a medium of refractive index mu at a distance S, this C times T corresponding to the distance in vacuum, or the equivalent distance in vacuum that particular light ray can travel in vacuum by covering the distance S in a particular medium. അതായത് ഒരു പർട്ടിക്കുലർ മീഡിയത്തിൽ മ്യൂ എന്ന റിഫ്രാക്റ്റീവ് ഇൻഡെക്സ് ഉള്ള ഒരു പർട്ടിക്കുലർ മീഡിയത്തിൽ എച്ച് ഡിസ്റ്റൻസ് ഒരു ലൈറ്റ് റേ ട്രാവൽ ചെയ്യുകയാണെങ്കിൽ അതിന് കറസ്പോണ്ടിങ് ആയിട്ട് വാക്വത്തിൽ ദാറ്റ് പർട്ടിക്കുലർ ലൈറ്റ് റേക്ക് ട്രാവൽ ചെയ്യാൻ പറ്റുന്ന ഡിസ്റ്റൻസ് ആണ് ദിസ് സി ഇൻറ്റു ടി. ഒരു പർട്ടിക്കുലർ മീഡിയത്തിൽ മ്യൂ എന്ന റിഫ്രാക്റ്റീവ് ഇൻഡെക്സ് ഉള്ള ഒരു പർട്ടിക്കുലർ മീഡിയത്തിൽ ഒരു ലൈറ്റ് റേ എസ് എന്ന ഡിസ്റ്റൻസ് ട്രാവൽ ചെയ്യുകയാണെങ്കിൽ ആ ലൈറ്റ് റേക്ക്, ദ പർട്ടിക്കുലർ ലൈറ്റ് റേക്ക് വാക്വത്തിൽ കവർ ചെയ്യാൻ പറ്റുന്ന ഡിസ്റ്റൻസ് ആണ് സി ഇൻറ്റു ടി എന്ന് പറയുന്നത്. സോ ദിസ് ക്വാണ്ടിറ്റി മ്യൂ ഇൻറ്റു എസ് ഈസ് കോൾഡ് ഒപ്റ്റിക്കൽ പാത്ത്. ഒപ്റ്റിക്കൽ പാത്ത്. Optical path. So mathematically we can represent this optical path as, it is the product of refractive index of a medium and geometrical distance. Geometrical distance traveled by light ray in time t. t സെക്കൻഡ് കൊണ്ട് ആ ലൈറ്റ് റേക്ക് ട്രാവൽ ചെയ്യാൻ പറ്റുന്ന ജിയോമെട്രിക്കൽ ഡിസ്റ്റൻസിൻ്റെയും ലൈറ്റ് റേ മൂവ് ചെയ്യുന്ന പർട്ടിക്കുലർ മീഡിയത്തിൻ്റെ റിഫ്രാക്റ്റീവ് ഇൻഡെക്സിൻ്റെയും പ്രൊഡക്റ്റിനെയാണ് നമ്മൾ ഒപ്റ്റിക്കൽ പാത്ത് ഓഫ് ദാറ്റ് പർട്ടിക്കുലർ മീഡിയം എന്ന് പറയുന്നത്. സോ ദ ഒപ്റ്റിക്കൽ പാത്ത് ഓഫ് എ പർട്ടിക്കുലർ മീഡിയം ഇസ് ദ പ്രൊഡക്റ്റ് ഓഫ് ദ റിഫ്രാക്റ്റീവ് ഇൻഡെക്സ് ഓഫ് ദാറ്റ് മീഡിയം ആൻഡ് geometrical distance traveled by the light ray in time t. So it is the optical path. This optical path has very important role in the field of geometrical optics and also particularly in Fermat's principle. So we are expressing the following terms in terms of this optical path, because the optical path is a constant, an important role and with a constant term in corresponding to a particular medium, and this represents or this relates the geometrical distance and time taken. So let us consider another medium. The property of that medium is, let us consider our starting point is P and the final point is Q itself. and this medium has some more points, some P1, P2, P2. So the light ray, a particular light ray travels from P to Q, P to Q through P1, P2, and from P to P1, let us consider the refractive index is, the geometrical distance is S1, and P1 to P2 geometrical distance is S2, and P2 to Q the geometrical distance is S3. And let us consider that this the medium or the distance P to Q is consisting of three mediums having values of refractive index mu1, mu2 and mu3. That is, from P to P1 the refractive index of medium is mu1, and from P1 the medium is changing and the second medium has a refractive index mu2, and again at P2 the medium is again changing and the final refractive index is mu3. The point here is that the changing of the refractive index at P1, P2, P1 and P2 at point P1 and P2 are abrupt, or it is not a continuously varying medium, but it is a medium having discrete values of refractive index mu1, mu2 and mu3. Then if a light ray travel from P to Q in such a condition, the total optical path will be, optical path is equal to, we have the optical path is product of refractive index and geometrical distance. It will be mu1 times S1 for first medium plus mu2 times S2 for second medium and plus mu3 times S3 for third medium. This we can write in a manner that it is summation from I is equal to 1 to 3 mu I times is I. Then in general, for such a medium having discrete values of refractive index, or refractive index is changing, abruptly changing, and having refractive index values mu1, mu2, mu3 etc., then we can write it as the optical path, total optical path is equal to summation I is equal to 1 to n mu I times Si. For a discrete value of refractive index, or a medium having discrete values of refractive index, we can write the optical path as summation mu I times Si. Now let us consider another case for which, if the changing of refractive index is not an abrupt, or the change of refractive index is continuous or continuously varying refractive index medium, a medium having continuously varying refractive index, and if a light ray is traveling from P to Q, as we mentioned earlier, P to Q, the refractive index is continuously varying, then for such a medium the optical path will be integral P to Q mu into ds, where ds is a small distance between P and Q, ds is a small distance between P and Q, and mu is the refractive index corresponding to the small distance mu, ds. The refractive index corresponding to ds is mu, then mu ds is the refractive index of the very short distance, and this quantity is repeating in all sections or subunits of P and Q, P to Q, distance between P to Q. Then the total optical path will be integral P to Q mu times ds. I think you have got it well. Then let us go to the Fermat's principle of least time. Fermat's principle of least time. Fermat's principle of least time describes the rectilinear propagation of light. Least time. It is the first principle in the three Fermat's principles or Fermat's laws, and this least time corresponding to the or explains the rectilinear propagation of light. First of all, I am stating the Fermat's principle of least time. That is, when a light ray travels from a point P to Q, it follows out of all possible paths from P to Q a path in which the time requires to travel from P to Q is minimum. Or when a light ray is traveling from P to Q, out of all possible paths from P to Q, the light ray will follows a path from P to Q in which it requires the least time. അതായത് if a light ray is traveling from P to Q, there are a lot of possible paths. We can mark these paths, or I am marking these paths are from P to Q. That is, this is one path, this is another path, it's a first path, it is a second path, and there is another path as like this, it is third path, and there is a lot of another paths. Infinite number of paths are possible between P and Q, but in this infinite number of paths, the light ray will choose a particular path in which the time taken to travel from P to Q is minimum, or light ray requires the least time for traveling from P to Q. So now we can express this in a mathematical way. As I mentioned earlier, let us consider v is the velocity of light ray. V is the velocity of light ray. V is the velocity of light ray, and mu is the refractive index of medium. Mu is the refractive index of medium, because this velocity is dependent to the refractive index of medium. If the medium will changes, velocity will also changes. And let us consider a particular path. Let us consider the first path or second path, either it is a distance, a small distance dl. Dl is a small distance in first path, and the light ray consumes a time dt to travel the distance, the small distance dl. So we can write it as dt will be equal to dl divided by v, or we have v is equal to c by mu. Dt will be equal to dl divided by c by mu, which is equal to 1 by c times mu into dl. Means dt is equal to, or time taken to cover the distance, small distance dl, is equal to 1 by c times the optical path. This quantity is optical path itself. Optical path itself. Then we are considering the propagation of light ray from P to Q. Then the total time taken to cover P to Q is, the total time will be to travel from P to Q is equal to, it will be T is equal to integrating from P to Q 1 by c times optical path or mu into dl. we can take the 1 by c outside the integral, where c is a constant, which is the velocity of light in vacuum, p into q mu into dl. Now we can choose another path between p and q. The property of that path is, let us consider the third path. As I mentioned here, 3, it is the this is the third path, as marked is in red color. So for this third path, the time taken for traveling from P to Q is minimum. The property of, let us consider, we are considering the third path, and the property of this third path, let us consider the property of this third path as the time taken to travel from P to Q is minimum. Then we are considered the third path, and the property of that third path is considered as the time taken for the traveling from P to Q is the minimum value, or the minimum time for traveling from P to Q is corresponding to the third path. So if you are consider any other path other than this third path, there will be a increase in time for traveling from P to Q. So this increase in the time for time to travel from P to Q other than the third path is or the time taken for traveling from P to Q other than through third path has a value greater than the time taken corresponding to the third path. So if we are considering or comparing the time taken for corresponding to time taken to travel from P to Q corresponding to the third path and all other paths or other paths, there will be a variation in time taken. There will be a variation in time taken. That is, for the third path, for the third particular path, which has the minimum time taken value, corresponding to that third path, this variation in time will be equal to 0. What I mean is, the third path corresponding to the minimum time and all other paths 1 and 2 having greater value of time than this time corresponding to the third value, then for comparing the time taken for first, second and third paths, the variation there will be a variation in time corresponding to first and second paths, and the minimum time is corresponding to the third path. So the variation corresponding to this third path will be equal to 0. That is delta t. We are denoting the variation as delta t. Simply the variation is nothing but the time taken, if we are considering the first path, the time taken for the first path is t1 and time taken for the third path is t3 and time taken for the second path is t2. Then we have this t3, value of t3 is the minimum value. Then the variation in time means that t1 minus t3 and t2 minus t3. That is the change in the time corresponding with respect to the minimum value of time. Minimum value il ninnu പുതിയ പാത്തിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള ടൈമിലേക്കുള്ള ഡിഫറൻസിനെയാണ് നമ്മൾ ഈ വേരിയേഷൻ എന്നതുകൊണ്ട് ഉദ്ദേശിക്കുന്നത്. So if you are consider the third path and the time taken for the third path is t3, then its variation is t3 minus t3 will be equal to 0. Delta t1 is equal to t1 minus t2 and delta t2 is equal to t2 minus t3 and delta t3 is equal to t3 minus t3 itself. So the variation is equal to 0. Now we are applying this variation value of time to this equation, then we will get which is equal to 1 by c times the variation in moving P to Q mu times dl will be equal to 0 because this dl is an arbitrary distance, and if the we are considering this arbitrary distance in the third path itself, so 1 by c is a constant and there is no variation in it. We can write it as delta of integral p to q mu dl is equal to 0. So we have the Fermat's principle states that the light ray will follow some paths in which the property of that particular path is time taken is least or time taken is minimum, or in other words the variation in time is equal to 0. We applied this variation in time to our theories, and we got that variation of time will be equal to 0 is equal or implies variation in the optical path is equal to 0. Then we can restate our Fermat's principle as light travels along a path in which time taken is minimum can be restated as light will travels along a path having the minimum optical path length, or minimum time, or light will choose a path in which minimum time or least time is also corresponding to light will choose a path, light will choose some path having the minimum optical path, minimum optical path. So we have our restated Fermat's principle as delta of integral p to q mu times dl is equal to 0. If we consider a homogeneous medium, such a medium will have same values of value of refractive index throughout. So this quantity mu will be a constant throughout that medium. Then we can take this quantity outside the integral as well as outside the variation. Then we get mu times delta of integral p to q dl will be equal to 0. Mu is never becomes 0, so we get delta of integral p to q dl is equal to 0. This equation means that the integral p to q dl is the total distance between p to q, and integrating this value we will get the total distance between p to q as we mentioned earlier. Then the variation corresponding to this total distance is equal to 0. That means this distance is nothing but the straight line distance between p to q. p യുടെയും q-ൻ്റെയും ഇടയിലുള്ള സ്ട്രേറ്റ് ലൈൻ ഡിസ്റ്റൻസ് ആയിരിക്കും ഇതെന്ന് പറയുന്നത് ഈ ഇക്വേഷൻ സാറ്റിസ്ഫൈ ചെയ്യുന്നത്, ഓർ ദിസ് ഇക്വേഷൻ വിൽ സാറ്റിസ്ഫൈസ് ഓൺലി ബൈ സം ഡിസ്റ്റൻസ് which is the straight line distance between p to q. So in conclusion, that means that Fermat's principle states light will follow the path for which the time taken is minimum, or minimum optical path means that light will chooses some path between p and q that is the straight line distance between p and q. Light will chooses the one and only path between p and q. That path is the straight line distance between p and q. In that manner, Fermat explained the rectilinear propagation of light. Rectilinear propagation of light. But in general, in our day-to-day life, we are familiar with a lot of mediums or a lot of optical devices which will not obey this Fermat's principle. That means we are familiar with spherical reflectors, we are familiar with lenses, and we are all familiar with plane mirrors. These are three kinds of objects or optical objects we are familiar with our day-to-day life. But in this case, the plane mirror will obeys the Fermat's principle, and it chooses or it allows the minimum path or minimum time to reach from a source to the observer. But for the case of a lenses, this lenses will chooses a stationary time other than the minimum time. For the case of spherical reflectors will chooses the maximum time to travel from a source to the observing point. So the property of the spherical reflectors is that if it chooses any path, the time taken is a stationary value. So that value will be the maximum than any other the minimum values, and lenses will choose as a stationary time and plane mirror will choose as a minimum time. So we can restate this Fermat's principle that for our day-to-day life or in general our experimental observations, this is a theoretical observation. The Fermat's principle is a theoretical observation, and in our experimental values or observations, this minimum time is not possible in all cases. Some cases will chooses the stationary time, some cases will chooses the maximum time. So we can restate this Fermat's principle that the light ray will chooses a path out of out of all possible paths the property of that particular path is that the time taken is extremum. That is, extremum means it can be minimum for the case of a plane mirror, or it can be maximum for the case of spherical reflectors, and it can be a stationary value. This statement that the light ray will choose a path out of all possible paths in which the time taken is extremum is called Fermat's principle of extremum path. Fermat's principle of extremum path. Fermat's principle of extremum path. Today I am concluding my lecture by this. If you like my lectures, please like and subscribe my channel. Thank you.